Good, good day. My name is Mr. Moses, your physics teacher. You're welcome to another class on physics. We treated in the last class elastic collision and inelastic collision. Now today we are going to do mechanical energy. As you can see on the screen, mechanical energy is the energy that is possessed by a body due to its motion or due to its position. But before we dive into mechanical energy, let us look at work. It said work is said to be done when a force travels through a distance in the direction of the force. What we mean here is that you can only say you have done work when you apply force on something, let's say an object, and the object moves in the direction of the force. That means whenever there is work, there has to be force and distance. A distance that is the same with the direction of the force. Hence, work done is the product of force, the force applied, and the distance moved by the force. So if I am pushing an object, if I'm pushing an object forward, it means I am doing work only when the object is moving forward. If the object is not moving forward, then I am not doing any work on the object. So work done, or work is only done when the force that is applied moves through a particular distance in the direction of the force. Take for instance the picture on your screen. The man is pushing the box. The only time that it can be said that he is doing work on the box is when the box moves in the direction of the force that he is applying. That is when work is said to be done. So mathematically, it is the product of force and distance. Work done is also described as force times distance cos theta, where theta is the angle of inclination of the force. Sometimes the force that is applied might be at a particular angle to the x-axis. If the force is not at an angle to the x-axis, it means that it makes an angle of theta with the x-axis, and theta will be 0, so cos theta would be 1. That's why most times we have that force times distance is equal to work done. And then we go to types of mechanical energy. We have potential energy and kinetic energy. It's something we already know of. We know that potential energy is the energy possessed by a body by virtue of its position. That means an object that is at rest possesses potential energy because of the state of rest that it is, because of the position that it is occupying. Energy is measured in joules, potential energy is measured in joules. Two types of potential energy is what we have. We have elastic potential energy, we have gravitational potential energy. And as you can see on the screen, elastic potential energy is the energy stored as a result of the formation of an elastic object. For example, the stretching of a spring. If you take a spring and you compress it, at that point that it is compressed, the spring has potential energy that is called elastic potential energy, such that if you release it, that potential energy that has been gained will turn to kinetic energy, since we know that energy is neither created nor destroyed but transforms. There you have your example. Even when you stretch the spring and hold it, you are creating potential energy in the spring, such that when you release it, that potential energy is converted to kinetic energy. So the energy that is stored in a compressed spring or an elastic body that is stretched is called elastic potential energy, and it has a formula of half kx squared, where k is the spring constant and x is the extension. Then we have gravitational potential energy, which is the energy stored in an object due to its position above the Earth's surface. When an object is at rest at a particular height above the Earth, there's what we call gravitational potential energy that it possesses because of its position. Mathematically, it is represented as the product of mass, acceleration due to gravity, and the height of the object. Take the picture on your screen, for instance. The ball of mass m is at a height of h above the ground. because of the position of that ball above the ground, it has what we call gravitational potential energy. That means that it has the potential to be released and drop in accordance with the pull of gravitation, of gravity. You understand? That's what we mean by gravitational potential energy. And then we'll go to kinetic energy, which is the energy possessed by a body because of its motion. For every object that is moving, for every object that is in motion, it possesses kinetic energy. And this kinetic energy is represented as half mv square, where m is the mass of the object and v is the velocity with which the object is moving. So you can see the kinetic energy is energy possessed by bodies that are in motion. And we also have examples of kinetic energy above: walking, falling, flying of a plane, throwing a ball. As far as movement is concerned in that object, it possesses kinetic energy. As far as it has movement, it possesses kinetic energy. So when the object is moving, it has kinetic energy. It is represented as half mv square, and its SI unit is in joules. Then we will now go to conservation of mechanical energy. This states that in a closed system, the total energy is always conserved but can be changed from potential to kinetic. Conservation in this case means that mechanical energy is not lost. When an object is at rest, it possesses potential energy. Once the object begins to move, that potential energy is changed to kinetic energy. So it doesn't lose energy, it is only a gradual change process. For instance, you have the picture above. The stone that is held up high, when it is held up, it possesses potential energy because it is at a spot. Once it is released, the potential energy decreases and the kinetic energy increases. Then just before it hits the ground, it possesses high kinetic energy. That means that the potential energy of the stone from the start, when it was held up, has been converted to kinetic energy. That's what we mean by conservation of mechanical energy, where potential energy is converted to kinetic energy and energy is not lost. We have the swinging of a simple pendulum. When it swings to the right or to the left, it attains a particular position before it returns back. Now when it stays in that position, it possesses potential energy. As it starts to return, potential energy reduces and kinetic energy increases. Overall, in conservation of mechanical energy, the value of the potential energy is equal to the value of the kinetic energy as it changes. And then we have examples. We have, if a force of 30 Newton moves an object through a distance of 4 meters, calculate the work done. We know work is force times distance, so we have 30 times the distance 4 to have 120 joules. You were not given theta here, and so it is assumed that cos theta is 1, because if theta is not given, it means that the force went in an horizontal way. That means it is of 0 degrees with the x-axis, and it is 1 cos 0 is 1. Here's another example. Calculate the potential energy of a mango hanging on a tree 7 meters tall if the mango has a mass of 2 kg. Potential energy is mgh, mass times acceleration due to gravity times height, and acceleration due to gravity is a constant, which is 10. So we have 2 times 10 times 7 to be 140 joules. We'll take one more example. For kinetic energy, we have calculate the kinetic energy of a car moving with a speed of 40 meters per second if the car has a mass of 50 kg. Kinetic energy is half mv square, so we have half times the mass 50 times the velocity 40 square, and we have 40,000 joules. Please do well to go through the leading questions, solve them in your notes. We will discuss them in class. Thank you very much. I'll see you next time.